Hello, this is David Shreeve, Algebra 2 instructor with Florida Virtual School. We're going to look at a couple of the problems with adding and subtracting radical expressions. To be able to do these efficiently, you will want to certainly know all of your perfect squares, and you want to be really good at breaking down the values into their factors. In other words, when I first look at my first term here, see, I've got 75x squared y. Well, I know x squared obviously is a perfect square. That will come out as an x. But the 75, I want to not only think of all the prime factors of 75, I want to maybe keep myself from having to go that far, and think of the fact that 25 times 3 would be 75, and this 25 is a perfect square. So in other words, I can pull that 5 out, and I can pull an x out there. Alright, so when we get to the 80, I want to think of perfect square that's a factor of 80 would be 16. It'll be 16 times 5. With 48, we also have a perfect square that's a factor of 48, which is 16 times 3. And then finally the 20, you just have 4 times 5 there, and the 4 being the perfect square. Okay? And from this point I can start taking out anything that I see is a perfect square. Well, where do we have perfect squares? Well, there's quite a few of them here. We've got here, here. And I'm just kind of making sure I mark these so I'm keeping track of what I pull out, and also I'm keeping in mind what is going to be left under the radical here. That's all of these values. Okay, there's nothing really I can take out on those particular values. Alright. So, moving right along, let's go ahead and pull out square root of 25 is, of course, 5. Square root of x squared is x, and then underneath we'll still have the 3y. Square root of 16 is 4. Square root of y squared is y, and underneath the radical we still have 5x. Square root of 16 is 4. Square root of x squared is x. Under the radical we still have 3y. And then here, square root of 4 is 2. Square root of y squared is y. And then under the radical, you'll still have a 5 and an x. Alright, now looking closely here, it turns out that we actually have some terms that we can combine, some like terms. And I like to mark those. I like to use different colored pens and pencils, but you can use whatever you like. You know, some students will maybe put a specific shape over the like term, so I might put a rectangle around those and maybe like an oval around these. Okay, meaning like terms that they have the same radical part. Okay, so these are portions that I can actually combine. In other words, 5x times the square root of 3y minus 4x square root of 3y. Now, we look at the radical portion just as an additional variable or anything. Really, all I'm doing is subtracting 4 from 5. So 5 minus 4. Alright. Well, 5x minus 4x is just 1x. So there would be an x left over. X square root of 3y. And then look here, negative 4y plus 2y. Well, that's going to leave me with negative 2y. Alright, and then that's as far as you could go on that one. So that would be our final answer on that one. And we're going to take a look at one more dealing with some higher order roots. I've gotten a few questions on some of the higher order roots. Okay, so let me just slide this up a bit here. Don't want to have any confusion, and this is not associated with what we're working on now. Okay, so what we're working on now, some higher order roots. So we're going to look at cubed root of 54 plus the cubed root of 16 minus the cubed root of 24. Now, when I look at this particular problem, I'm going to do the same thing that I did with my square roots. I'm going to think of perfect cubes. So when we think of perfect squares, all right, we think, okay, well, 1 squared is 1, 2 squared is 4, 3 squared is 9. You know, just going up, 16, 25, 36. Those are my perfect squares. So when I think of dealing with square roots, I'm looking for any of these values that might be factors. When I'm dealing with cubed roots, though, I have to think of my perfect cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and so on. So I want to look for these values that are factors of the number. So obviously the 64 I won't be using with any of these, but you'll notice this first value I have is 54. Well, that's just 2 times 27. So here we have the cubed root of 2 times 27. So as I said, I'm thinking of a perfect cube that's a factor of this value 54. In other words, meaning that's 3 times 3 times 3 is 27, meaning the cubed root of 27 is 3. All right. So here, 16, if I look at my list of cubes over here, well, I certainly see the 8. Well, the 8 obviously is a factor of 16, so that would be cubed root of 2 times 8 minus the cubed root, and 24. Well, there's 27 here. It's too large to be a factor, but 8 is a factor because 3 times 8 equals 24. Now, I'm going to go ahead and take a moment to identify my perfect cubes that I'm going to be able to take out, okay, from under this cubed root radical. So once I identify those, I can also see what's going to be left underneath the radical here. Okay, you don't really typically need to identify those when we're only dealing with 2 factors here. So, all right. Now what we're looking at, cube root of 27, of course, is 3. So we have 3 times the cube root of 2 was left under that radical. All right, plus, now 8. The cube root of 8 is 2, because 2 times 2 times 2 equals 8. So that's 2 times the cube root of 2, remember the 2 staying under, okay, minus, and here we have also an 8 that will be pulling the cube root of 8 out. So again, that's 2, and then we have the cube root. Here we have a 3 underneath. This is another good example of, you know, exactly how are we going to deal with our like terms. You know, you think of these radicals exactly the way you think of a regular variable. In other words, they have to have the same exact radical part to be like terms. So I can only combine what I have here at the beginning because they both have the cube root of 2. This is cube root of 3, so it is not a like term that can be combined. So here all I have to do is add my coefficients, 3 plus 2. That gives me 5 times the cube root of 2 minus 2 times the cube root of 3. That would be my final answer. There's nothing else I can simplify from that point on that, okay? So that's just a couple of the radicals, one with the higher index there, the cube root. Hope this helps.